Ladies and gentlemen, we'll continue with the Frontier of Science award winners. So the next speaker will be Bernardo Cockburn from the University of Minnesota, and today he will talk to us about bridging the hybrid high order and the hybridizable discontinuous Galerkin methods. All right, let's welcome him.
Yeah, thank you very much. What I will what I would like to do today is to tell you something about an unexpected collaboration I had with Daniele Di Pietro, who is in the Alexander Grothendieck Institute in Montpellier, and with Alexander Earn, who is in the École Nationale des Ponts et Chaussées in Paris. And I was working on hybridizable discontinuous Galerkin methods. They were working on the hybrid high order methods, and then we got together and showed the relations between these two methods. So that's what I plan to show you how do you do that. So I'm going to describe the model problem, and the model problem is going to be a very simple diffusion equation, and both methods are going to be defined there. I'm going to show you how to define the HHO method and then how to define the ATG methods. And then I am going to build a bridge between them. I'm going to start with the HHO, and I'm going to change it slowly until it becomes an ATG. And once we are there, we are going to be able to compare the methods and see how some of the properties of the HHO can now be incorporated into the ATG method and vice versa. And then I'm going to show you that new HHO methods and new ATG methods can be obtained thanks to this comparison. And to end, I'm going to say something about the consequences of this relation. Okay, so this is my framework. Kappa is, well, this is a standard elliptic equation. You can think of U as the temperature and of minus kappa gradient U of like the flux, the temperature, the heat flux. Okay, so in this simple setting, where I'm going to show you the HO method, but before showing you the methods, I have to say that it was introduced, these HHO methods were introduced by Daniele Di Pietro, Alexander Earn, my collaborators, and Simon Lemaire in 2014, 2015 into a couple of papers. And what is very nice about these methods is that they are defined in arbitrary meshes, in very general polyhedral elements, and they are optimally convergent, and they achieve that with the smallest spaces than in any other method. So this is they have a very special property, which is this one. Okay. All right. So now let's get into business. So okay, so this is a little bit complicated, so I'll spend some time doing this. So let me see. Okay, so this tau means the collection of all the elements, and we are going to partition the omega, the domain omega, into elements, and F are the phases of the elements. So V sub tau is the part of the function that is defined inside the element, and V sub F is the part of the function that is defined only in the boundaries, okay? So, and then we pick two spaces. One space is typically polynomials of degree L inside the elements, and here polynomials of degree K on the boundaries, and they are discontinuous. They are completely discontinuous. So since they are discontinuous, this method is part of the discontinuous Galerkin methods. And so it is defined, the method is defined this way. First of all, with Vt inside, this is the part of V that is inside the element. You can see this is the integral over the element, and this is the integral of the boundary of the element. So with this Vt and V in the boundary, which belongs here, then we can compute an approximate gradient. So this is an approximate gradient, which lives not in pk or pl, but in pk plus 1. So it's a little bit higher order than V here. So and then this equation doesn't determine the constant, and so here we have to add an equation to determine the constant. So the constant of this guy is equal to this thing. The constant of this thing is equal to that. Okay, and then it's not very difficult to show that this is well defined. So in order to continue, we have to given this V, we have to define an approximate gradient. That does P of V bar, this is our approximate gradient. Okay. So the HHO approximation, we can define it now as U. Oh, this is a typo. This U, not W, that belongs to this space. And this is the solution of this problem. AT is a bilinear form, and this is just the L2 inner product of F and Vt. And this bilinear form is kind of tricky, so bear with me. It has two parts. The first part is kappa, the gradient of U, so this gradient here of U, and times the gradient of V. V is a test function, but it satisfies this equation. So this is the part that gives consistency to this term. And then I have to add a term that is called the stabilization term. You can see the stabilization term depends on some projections. This is a projection into the space UK. So it's a projection on the border into polynomial degree K. And this is a parameter that we can define. And so here we have this parameter times this projection times this distance, and again this times that. So we do that, or they do that, they did that in order to maintain symmetry. So here you can see that you can interchange U and V and you get the same. You interchange U and V and you also get the same thing. So this is a symmetric problem as we expect. And the tricky part is that this P is not the same as this one. So this P is what makes this method different. This P is associated with little p as follows. So this is Vt. So remember that this Pt is an approximation to U in the border. This guy here is a combination of Vt inside the element plus this guy here. And this is a projection into polynomials of degree L. Okay, so this is very complicated, but let me revise it for you again. We begin with giving two components of the approximation to the potential, to the temperature. With these two, with these two components, we create an approximate flux, heat flux, and then we use this thing to define the weak formulation. Here we have kappa, Pu, Pv, and then the stabilization Ut. This is again, this is for consistency consistency purposes, and this thing is to stabilize the method. Okay, and then look at this part here. We have P, this complicated P minus U, which is all this stuff minus. Okay, so let's leave this for the moment. I'll come back from time to time to try to understand this a little bit better. Okay, so now I'm going backwards. Okay, so now let me say something about the HDG methods. The HDG methods have a long history. If you are familiar with the discontinuous Galerkin methods, these are methods that were introduced back in '73 by people working in Los Alamos, and they were working on transport equations and bombs, essentially missile, things like that. Problems, hyperbolic problems, where you have convection as the main physical component. And so these methods were developed by Shu Wan and myself during the 90s. And then at the end of the 90s, it became clear that they were interested, they were going to be interesting to be applied to compressible object stocks. And so there was an enormous interest in extending the definition of these methods from the purely hyperbolic case to the elliptic case, because as you might know, the effects of viscosity and heat transport are modeled by second-order elliptic equations. So with Q1, we started to defining these methods, as you can see, in 98. Then we analyzed the methods with my student and my postdocs in 2000. And there was a paper I should have put there about a unification of many methods that were being created or remembered from the early 70s and in a unifying framework. But this paper doesn't really belong to this part of this story. What I want to say is that instead is that with Jacob Alaklishan, we took the mixed methods, which were methods that had been already there for a long time, and we hybridized them for the first time, and we show a lot of characteristics that were very interesting. In particular, we showed that they could be statically condensed, and I'm going to say something about that for those who don't know the term a little bit later. So sometime not very late after that, we got together with Raicho Lazarov, and then we extended this technique of static condensation to discontinuous Galerkin methods. And we showed that not all discontinuous Galerkin methods could be hybridized and then statically condensed, but there was a subset of them which became the hybridizable discontinuous Galerkin method. And this is the paper in which we introduced the methods, and this is an example of application to the elasticity. Then another thing I want to say is that Kikuchi and Oikawa, unknown to us, they were working on similar things, similar methods, but not using the same formulation that we have. And then they were using they were not using the flux. They were using just U, and they were using what the HHO people were using. And Lehrenfeld and Scherbel in 2010, they introduced a very interesting projection I'm going to mention later. And then Oikawa did the analysis of that projection in 2015. So let me show you now what these methods look like. They look like this. So here we have Q, U, and U hat. So Q is the approximation of the heat flux. U is the approximation of the potential inside the element, and U hat is the approximation of the potential on the boundaries of the element. So these things correspond to the HHO as follows. Got stuck there. Oh, there. Oh. Okay, so this is Q, this is minus Q, this is U, and this is U in the boundary. So we have very different notations, but I want to establish a link between them. And okay, so that's the first time I'm going to come back. I'm going to come back many times. So hang in there. So the first equation that we see here corresponds exactly at the first equation they have there. So here you can see that with U, the approximation of U inside the element and the approximation of U in the boundary, we compute an approximate flux. That's exactly what they do there. And then here we have an equation that says that the discrete divergence of Q is equal to F. And this is the form of Q hat. And you can see here that all these three equations, they are completely local. They are local to the element tau, T, right? So this means that if I am sitting on a face, I'll have two values of Q hat, one from the left of the face and one from the right from the face. So I have two of them, and for physical purposes, we want them to be the same. So this means that W hat times the jump of this stuff, so Q hat from one side dot n plus Q hat dot 1 from the other side, this jump has to be 0. So this enforces the uniqueness of the numerical flux. Okay. Any question? Yes. Yeah. Okay. So the LDG cannot have this form. You can see that here. Okay. So let me put it this way. Suppose that alpha is a constant. Then this method here, this is an LDG. This is an LDG flux on this tau, on this thing. So this does use the LDG element-wise. However, when you impose this condition, then you will have this Q hat has essentially two formulas, right? One from the plus side and the other from the minus side. And when you force them to be the same with this equation, then you have one equation, you can solve for that, and then you will see that the Q hat that is obtained is not an LDG. So that's what happens. First of all, in the LDG, you have to, in the LDG, this Q hat, let me see. Okay. This U is not clear from this formulation, but for the LDG, this U hat is independent of Q. And then you can eliminate Q from the equations and get an equation for U only. Now, if you use this formulation, what you can do is you can eliminate, you can consider U hat to be data. And then since this is data, it's like this problem is a discrete version of a Dirichlet problem. Okay, and then you can write QH and UH in terms of U hat using this thing. Once you have that, then you know that this guy depends on U hat only. And this is the equation that is globally coupled, right? So that's what is called static condensation. So you consider that this is data, you write this guy and this guy in terms of U hat, and then you have a single equation for U hat. So you eliminated QH and UH from the equations, and you have an equation that is much smaller just for the U hat. So this unknown is called the hybrid unknown, and a scheme like that is called hybridizable. Now, let me write for you very quickly here. Maybe I have time to do that. No? Here. Thank you. Okay, so suppose that you have Q hat n plus and then you have U minus U hat, and you also have the Q hat minus so both U hat is single valued, right? Single valued. Okay, so now I add these equations, and I want this plus this to be 0. Okay, so this is 0, and this plus this I call the jump of Q, and then here I have alpha plus U plus. Let's see. I'll stop this for a second. Okay, and then you see that U hat has to have this particular form. So in particular, U hat is equal to alpha plus U plus alpha minus U minus, and then plus 1 over. I thought I had turned this off. Okay, so for this term is equal to 0 for the LDG. So you can see that if the alphas are not infinity, which is pretty iffy to do, then this is not an LDG. And then the good news is that LDG method gives better precision than the previously known DG method. So that's why they were. So the HDG was devised in such a way that you can do static condensation immediately. You don't have to think about that. And you can extend this technology for any PDE by doing the following. You give the data is what allows you to solve a local problem, and then you have this transmission condition that defines. So this is a local. This unknown is data for the local problem, and this is an unknown for the global problem. And you can do that for any PDE. Okay. Any other question? Let's see, how am I doing time-wise? I'm okay. Let me know. Okay. So so this is the structure of and you can see that this is a very general structure because we can pick any V, any W, any M here for U hat belongs to M, and any alpha. So you can generate all these methods by changing the spaces and alpha. Then of course, if you are not careful, you don't get anything good, but potentially you can get very good. Okay. So that's that. Hmm? I'm sorry?
You still have 20 minutes.
30 minutes? Okay. 20? Okay. Okay. All right. So, okay. So this is the method. And now I'm going to go back to the HHO. And then I'm going to start with the first equation. This is the HHO. And I'm going to do the following. So I just copy the first equation, which I don't have to change. But here, I'm going to do the following trick. The test function here is going to be only the test function associated to the interior of the element. And everything in the boundary is going to be 0. Here, I'm going to do the opposite. So the test function associated to the interior of the element is 0, and the function in the border is going to be taken in a general way. So let me go back again. So you see here that I have, no, I have something here and something there. Okay. Here I have something, the test functions are in V bar, and V bar is this in the interior and this in the border. So I'm going to take first V tau 0 and then 0 V tau. So I do that. So this blue equation becomes 2 equations there. And now what I have to do is what I'm going to do is I'm going to work on these 2 equations. Right? And then what I want to note is that the first equation is going to tell me information about who is F. F is the divergence of Q. So since F is the divergence of Q, this has to give me something related to grad. And then the second equation, you see the second equation only depends on V on the boundary. So I have something on the boundary only. So it is reasonable to expect that only boundary integrals are going to happen there. And so this equation has to be equivalent or has to be related to the red equation. In the red, you see the only part that we have this W hat is the red equation. And in the HHO, that's exactly what happens in this equation. So my claim is that I have to wait for this. There's a delay, right? There. So my claim is that this equation is going to give us who is the divergence of Q here equal to F, and this thing is going to uncover for us the Q hat associated to the method, to the HHO. Let me try to show you that. So let's work on the red stuff, and I'm not going to go into the details, but let's proceed this way. So first of all, we have, this is by definition of A. So A is this grad, UT, and 0 VT because of that. So this is the consistent part, and this is the stabilization part. And now I use the definition of this to write this, okay? So this comes from the first equation. I know it's difficult to see. come from this equation. So if where's my stuff here? If I set b this guy equal to 0, I will have this term plus the other one. And that's exactly what I have. Where's the thing? No, that's not that. Oh, no. I'm confusing myself like this on tomorrow. There. So, okay, so I go from here to there by using the first equation they have, and then I just leave it like that. And to go from, and then I go from here to there by using who is P, by using who is this P and who is this guy. So again, this is difficult to see, but you can check the algebra. It's a very simple algebraic stuff. Let me show you this. Okay, so you see here, P is all this stuff. So for example, P of 0 Vt in the border is going to be 0 plus something like that. And so if you put that information in the equation I had, you get that. Okay, so maybe it's not worth trying to follow this complicated formula. I guess I made a mistake, but anyway, the point is that you can see here we have V in the border, and we have V in the border, and so we have something times V in the border, something else times V in the border. This operator here, we take the adjoint and put it there, and then what we get is we factor out V in the border, and we get V in the border times something, and this something has this form. And this is exactly the numerical trace that we were looking for. So, no. So instead of this equation, I can replace this by that. I'm going to do that next. There. Okay. Now I have to do something similar with the other equation, and I'm going to go fast because it's the idea what counts. So I start by putting the definition of this thing. This is by definition. This is the consistent part, and this is the stabilization part. And then here, to go from here to there, I use who is this P, give me this horrendous stuff. And here I use who is this P, and we get this stuff. So we have this thing plus that is Q, and these two terms are this. So I have grad plus Q. And I can now I can rewrite the second equation like that. Here it is. So I have grad times Q hat minus Q hat. So this is the equation divergence of Q equal to F. This is the equation that says Q is minus the gradient of U essentially. And this is the equation that says that the two Q hats have to be the same. So I have done that. So this is the recasting of the HHO method as an HDG. So we can see here that this is the transmission condition that says this Q is has to be single valued. This is the discrete divergence, and this is the fact that this is the discrete gradient. So, Okay, so then originally Daniele Di Pietro, Alexander Ern, and Lumiere, they use this scheme here. This is L, and this is K. So they here we can reinterpret the scheme as taking the spaces Vt as kappa grad of pk, and then this is the pk that we use, that we have used in there. And we can compare with the old method, the LDG, that has these two. You were asking about the LDG. So they have different spaces. This space is much smaller than that. This space is a little bit bigger, but not too much. Oh, well, no, in the same space. And so they can achieve k plus 2 instead of k plus 1. So we cannot achieve that much. And then there are variations of the HHO. This is new, and this was some scheme done by Mancini, I think, and yeah. Yeah, because this is okay. Yeah. Okay, so in all this table, all the elements have U hat in pk. The U hat, right there. Remember this guy? No. Okay, so this guy for the HDG, and for the HHO, it is where's this guy? It is this guy, this guy. So for the HDG is this guy, and that's what we solve for. We solve for that. This is the guy who has all his degrees of freedom globally coupled. Okay, so for all, in the table I show, let me see. In the table I show, all the U hats are in the same space. Okay, so all U hats are in pk. So essentially this means that the computational complexity is the same for all the methods, because this is what is really difficult to find. The local solvers, the local problems, you can solve in parallel. So some of them are bigger than the others, but this doesn't really impact the global count. If you, it's the same. It's the same condition number. For all, the order of the condition number is h to the minus 2. So, which is what you expect for elliptic equations. Yeah. So, grosso modo. So it's h to the minus 2. So all of these methods have essentially the same computational complexity. So where you can see the advantage of one over the others is the order of the accuracy. So for if you just take pk as we used to do in the LDG, then you just get k plus 1 instead of k plus 2. Yeah. And so the comparison between these two types of method allow us to identify the numerical trace in the HHO, which is important for practical applications too. And then, on the other hand, allow us to incorporate into the HDG setting this special stabilization that is more accurate, that gives more accuracy. And it also allows us to produce new HDG methods and one new HHO method. This one? Or this one? No, this one? This one? L is Lipitov and Mancini. I'll give you the names later. Yeah, it's no. They have in 14 they obtain a method that they call a mimetic method, and then we just show that it's kind of the same method. Okay, any other question? Yes, of course. Yeah. Um, okay, so if that's a tough question. If you if you can align the mesh on the discontinuity, then you don't see any problem. Very smooth. But if you cannot do that, it's very complicated. Even for the standard methods, so this doesn't get away from that. Any other question? Okay, so let me conclude. So we have seen that how to fit the HHO and the HDG framework. We have identified the HHO numerical trace, and the HHO stabilization has been incorporated, can be incorporated into an HDG method. And since now we have the divergence, the numerical trace of the HHO, there are post-processing techniques that allows us to get a H-disconforming flux. New methods were introduced, and this can be extended to any other PDEs. So that's at the end of the talk.
Okay, let's take the speaker.
Any questions?
So, if you have any questions, please go ahead. Yes.
So thanks for the nice talk. I'd like to ask what role does alpha play in the scheme and how to choose it in practice?
I'm sorry?
What role does alpha? There is primary alpha in your scheme, right? In the HHG scheme?
What happened with R?
Alpha.
Alpha?
Yeah.
Alpha is R. Alpha is, okay, so, yeah, that's a good question. It's a typo. The alpha is this guy. Alpha is this is some, in all this case, we take tau to be a multiplication.
Ah, I see.
Yeah, but yes.
In the original scheme?
Okay, so let me go. Let me see if I can be a little bit more precise about that. Okay, so let me see. It's a little bit more complicated than what I said. So
Yeah, here.
okay,
The
so
third equation.
all right. So Q hat is Q plus alpha of that, right?
Yes.
Okay, so for the HHO, alpha is complicated. So let me see. Let me get to the HHO. Okay, there we go. So you see that Q hat, oh no, sorry. No, just hang it there. Okay, here. This Q hat is Q plus alpha U minus U hat. So for the
operator, right?
For all these methods, this alpha becomes just a multiplication, like tau. But for the HHO, it had this special structure. This is the alpha of the HHO.
Okay, so it's an operator, right?
Hmm?
It's an operator.
It's an operator, yes.
Oh, okay, I see.
Yeah, this can be any linear operator.
Ah, I see.
Yeah. So for the HHO is this this is the transport of that, and this is a multiplication. So this is a symmetric operator, and you can prove that it's positive definite. Positive definite.
Ah, I see. Sorry, I thought it was a parameter. Sorry.
It is actually a stabilization, yes.
So, does the QH height really exist as a function?
It has the stability, yeah. It had the right stability, and thanks to that stability, gets optimal convergence. Yes.
Okay, so the last question. So, what could you tell us the advantages and disadvantages of the HHO HDG method comparing to the local DG method?
Yes. Yeah, you can see that if you, okay, so for general polyhedral, the HHO has one single recipe, and it works for any polyhedral element. If you try to do that for the ADG, you will see that for triangles is optimal, for simplexes is optimal. You don't have to add anything like that, but it's not optimal for any polyhedral. So there is something that has to be improved there. And what the HHO people have done is they show how to increase the accuracy by coming up with this special stabilization. Yeah. Yes. Does this answer your question? Okay.
Other questions, please.
So if we consider the time problem, evolution problem, for example, the parabolic or convection diffusion problem, does it work?
Yeah, it's the same.
Same.
Yeah, it's the same idea. Yes.
If there contains some convection terms.
Yes.
I mean,
it has been extended to convection too.
But the question is, for example, if the convection domain problem, right? There could be some very,
well, this is a discontinuous Galerkin method, and the discontinuous Galerkin method were originally devised for convection.
Right.
So there's no problem with convection.
Okay.
Yes.
Thank you.
Does this answer your question? Yes. So,
somebody.
Yeah, so I think my question is similar to the previous one. So when we say this method can be extended to other PDE,
I don't hear you.
So I mean, when we say this method can be extended to other PDE, is there any constraint?
Okay. Maybe, I don't know. I mean, if you have PDEs in divergent form, it's very easy. Because you essentially what you do here is you write, for example, for the HDG, right? You write all the equations as a first linear system, and then you apply the technique. I mean, let me show you here. Okay. All right. So you see, the first equation is this term is equal to divergence, the gradient of u. You integrate by parts, and you put a little hat in the trace. So here, the same thing, you have divergence of q, integrate by parts, and you put a little hat. And then the name of the game is to find the relation between q hat and q, and u hat and u, which is through this alpha. And then you might have to make sure that this is well defined, and that's it. And then you impose the corresponding transmission conditions. So if you have, so this mimics what the PDE does. So if you have a PDE that can do that, you can apply this immediately. Now, if you have equations in non-divergent form, for example, the Hamilton-Jacobi equation, things like that, you have to be more careful. So I cannot give you a general recipe, but yeah, people have done this. Yeah, but it's more difficult. Yes. Yeah.
Other questions? Well, if there are no other questions, let's thank Bernardo again.
Thank you. All right.